we previously talked about the importance of allowing CPD representations that encode additional structure in the local dependency model of a variable on its parents. And we talked about the case of tree CPDs, which allow us to depend on different variables in different contexts. But none of that helps us deal with the situation that we used as a motivation for this, which is where we have a variable such as, for example, cough, that depends on multiple different factors: pneumonia, flu, tuberculosis, bronchitis, and so on and so forth. This doesn't lend itself, say, to a tree CPD, because it's not the case that you depend on one only in certain contexts and not in others. Really, you depend on all of them, and all of them sort of contribute something to the probability of exhibiting a cough. So one way for capturing that kind of interaction is a model called the noisy OR CPD. And the noisy OR is best understood by simply considering a slightly larger graphical model where we break down the dependency of y on its parents x1 up to xk by introducing a bunch of intervening variables. So let's imagine that this is, again, like cough variable, and this is different diseases, for example. And what we're doing here is we're introducing an intermediate variable that captures the event that this disease, x1, if present, causes a cough by itself. So this is x1 by itself causes a cough, or causes y. You can think of it, each of these as a noisy transmitter. If you have the disease, say if x1 is true, then z1 sort of says, fine, x1 succeeded in its intent to make y true. x2 has its own little filter called z2, and z2 makes that same decision relative to x2. And so ultimately, y is true. So y is true if someone succeeded in making it true. Which means that y is a deterministic OR of its parents, z1 up to zk, z0 up to zk. So now let's make this a little bit more precise. So the probability of zi being true given xi, there's two cases. If xi equals 0, well, xi isn't even trying to make zi true. So in this case, the probability of zi equals 1 is 0. Okay? If xi is not true, zi doesn't get turned on ever. If xi is true, then there's some probability for zi to get turned on, and that probability is something called lambda I. And lambda I is in the interval 0, 1, and you can think of it as defining some kind of penetrance of how good is xi at turning y on. So if we actually write this down as a probability, and we just consider the CPD of y equals 0, so y doesn't get turned on, given some set of cases x1 up to xk. So now we're asking, what is the probability that all of these guys fail to turn on the variable y? So what I forgot to say is that z0 is what's called a leak probability, and that's the probability that y gets turned on just by itself. And that happens with probability lambda 0. So when does y fail to get turned on? First of all, when it doesn't get turned on by the leak, so that's 1 minus lambda 0, times the probability that none of the causes that are on, so none of causes that are on, which are the xi's that are equal to 1, turn y on. And so that's a product of 1 minus lambda I for all of the xi's that are on. So that gives us the probability of y equals 0, and obviously the probability of y equals 1 is just the complement of that, 1 minus. Sorry, this should be. So that's the noisy OR CPD. And you can generalize this to a much broader notion of independence of causal influence. This is called independence of causal influence because it assumes that you have a bunch of causes for a variable and each of them acts independently to affect the truth of that variable. And so there's no interactions between the different causes. They each have their own separate mechanism, and ultimately it's all aggregated together in a single variable z, from which the truth of y is then determined from this aggregate effect of all of the effects zi's of the different causes. So one example of this is we've already seen the noisy OR, but you can easily generalize this to a broad range of other cases. There's noisy ANDs, where the aggregation function is an AND. There's noisy maxes, which apply in the non-binary case when causes might not just be turned on or off, but rather they have different sort of extents of being turned on, and then Z is actually sort of the maximal extent of the independent effect of each cause, and so on. So there's a large range of different models, all of which fit into this family. Noisy OR is probably the one that's most commonly used, but the other ones have also been used in other settings as well. One model that might not immediately be seen to fit into this framework, but actually does, is a model that corresponds to the sigmoid CPD. So what's a sigmoid CPD? A sigmoid CPD says that each xi induces a continuous variable which represents wi xi. So imagine if each xi is discrete, then zi is just a continuous value wi which parameterizes this edge, and it tells us sort of how much force xi is going to exert on making y true. So if wi is 0, it tells us that xi exerts no influence whatsoever. If wi is positive, xi is going to make y more likely to be true, and if wi is negative, it's going to make y less likely to be true. All of these influences are aggregated together in this expression for the variable z, which effectively adds up all of these different influences plus an additional bias term, w0. And now we need to turn this ultimately into the probability of the variable y, which is the variable that we care about. And in order to do that, what we're going to do is we're going to pass this continuous quantity z, which is a real number between negative infinity and infinity, through a sigmoid function. The sigmoid function is defined as follows, and it's a function that some of you have seen before in the context of machine learning, for example. So sigmoid takes the continuous value z, exponentiates it, and then divides by 1 plus that exponent of z. And since e to the power of z is a positive number, this gives us a number that is always in the interval 0, 1. And if we look at what this function looks like, it looks like this. So this is the sigmoid function. The x-axis here is the value z, and the y-axis is the sigmoid function. And you can see that as z gets very negative, the probability goes to 0. As z gets very high, the probability gets close to 1. And there's this interval in the middle where intermediate values are taken. So this is kind of like a squelching function that sort of squashes the function on both ends. Let's look at the behavior of the sigmoid CPD as a function of different parameters. So here is a case where all of the xi's have the same parameter w. And so what we see here is the value of this parameter w, and over here is the number of xi's that are true. So let's look at first this axis over here. The more parents that are true, the more parents that are on, the higher the probability of y to be true. Okay? And this holds for any value of wd because these are all positive influences. Okay? So the more parents are true, the more things are pushing y to take the value true. This axis over here is the axis of the weight, and we can see that for low weights, you need an awful lot of x's to get y to be true, but as w increases, y becomes true with a lot fewer positive influences. This graph on the right now is what we get when we basically just increase the amplitude of the whole system. We multiply both w and w0 by a factor of 10. And what happens is that means that the exponent gets pushed up to extreme values much quicker. Z gets effectively multiplied by a factor of 10, and that means that the transition becomes considerably sharper. That gives us a little bit of an intuition on how the sigmoid function, on how the sigmoid CPD behaves. So what are some examples of this kind of an application of this? So I showed this network in an earlier part of this course. It's the CPCS network, and it's used for, it was developed for here at Stanford Medical School for diagnosis of internal diseases. And so up here we have things that represent predisposing factors. And there's actually a fairly eclectic range here. So, for example, one predisposing factor is intimate contact with small rodents, because that's the contributing factor to hantavirus. And so there's a whole range of predisposing factors. Down here in the middle, we have diseases. And down at the bottom, we have symptoms and test results. Now, as I previously mentioned, there is approximately 500 variables in this network, and they take on average about 4 values. So the total number of entries in a joint distribution over this space would be approximately 4 to the 500 different parameters, which is clearly an intractable number. If we were to take this network and if we take this distribution represented using the network shown in this diagram, we get considerable sparsification, and the factorized form has approximately 134 million parameters, which is still much too many to have a human estimate. By using, as in this case, they used a noisy max CPD, they brought the number of parameters to about 8,000 total parameters for this network, which is a much more tractable number to deal with.